Yes, lab is at normal time at 2. Okay, let's get started. So this is chapter 19. It is about optical devices, optical instruments. It's basically the application of what we learned so far about refraction, reflection, all those kinds of things, lenses. Okay. So one of the applications is magnifier, magnifying glass. So when we talk about magnification, if you guys remember, magnification is, we can find magnification by using this formula. So magnification, M is the height of image over height of object. Or you can also find it by taking the negative ratio of image distance over object distance. Okay. Now there is another kind of magnification we are going to talk about. Okay, so that is called angular magnification. So this is one way, but there is another way we can find magnification, which is the ratio of angle subtended with the aid of lens, which we call theta, and angle subtended without the aid of lens. Okay, so we'll talk about what these things are. This is called angular size with lens, and this is angular size without lens. It's basically the ratio of size, two sizes. In this case, we can take the ratio of angular size instead of the linear sizes. So these are the linear sizes, but now we are talking about angular sizes without lens. Okay, so let's see what those things are, theta and theta naught. So when we look at an object, the size that we perceive with our eyes depend on the image that is formed in our retina. Okay, so you see we have the image on the retina. Although these objects are of the same size, okay? So if you compare this, the height of the objects, they have the same size, but the image they form on the retina have different sizes. One is bigger than the other. And the image formed on the retina depends on the angle subtended by those objects on our eyes. Okay, you see here, this one, green one, subtends that angle, this green angle, and this red one subtends this red angle. And if you compare this green angle with the red angle, you see that the red one is bigger than the green one. You see here, this angle, red one, is bigger than the green one. So the size of the image formed on the retina depends on the angle subtended by the object on our eyes. Okay. And these angles are called the angular sizes. Okay, so this is the angular size of this object, and that's the angular size of this object. And the angular size depends on the distance between the object and the eyes. Okay, farther the object, smaller is the angular size. Closer the object, bigger is the angular size. Now, if the angular size is same, no matter how big or small the objects are, they will appear to be of same size. So you have a small object and a big object, but they subtend same angle to the eye. Okay, here you have same angle subtended by those objects, and they will appear to be of same height. Okay, because they subtend same angle. So if we look from the Earth, the Sun and the Moon appear to have same apparent size, even though Sun is 400 times bigger than the Moon. And the reason is Sun and Moon basically subtend same angle to our eyes. So what's the maximum angle we can see? A maximum size of the angle that we can see for any object. So let's consider an object. Okay, let's see if I could write on. So we have an object, and let's say we move this object closer and closer to the eye. Okay, so initially it's here. Now let's move it closer and even closer, and then even closer. Okay, so if you compare the angles of all these objects, you see that's the angle subtended when the object is at that distance, and that's the angle subtended when the object is that distance. And as you move it closer and closer, you see the angle gets bigger and bigger, right? So this is the angle when it's here, that's the angle when it's here, and this is the angle when it's here. So the image formed on the retina gets bigger and bigger when you move the object closer and closer. But there is limit to that, okay? Because we know that if you saw the last lecture, our near point is 25 centimeters. Anything that is up to 25 centimeters is seen very clearly. But if we move the object closer than that, we'll have hard time focusing that. Okay? It'll look a little bit blurry. So our limit to view the object clearly is up to the near point. Okay? And although if you move this object closer than that, although it may subtend bigger angle, but we won't be able to see it clearly. So this is the limit. Okay? So at this point, the object that we see would have the maximum angular size. Okay? So this is the point where we see maximum height clearly. And the angle corresponding to that is called maximum angular size. Oops, it's hard to draw a straight line. So, okay, so this is the angle, maximum angle that we can see clearly. Now, if we look at this triangle, look at the triangle. If I take the tan theta of that triangle, right triangle, tan theta would be ratio of this height opposite over this base, which is 25 centimeters, which is the near point of our eyes. Okay, and if we consider this angle to be a small angle, okay, this is true for any kind of small angle. If the angle is small, which means less than 5 degrees, then we can write sine theta is equal to theta. Also, tan theta is equal to theta. Okay, this is true for small angles. Small angles means less than 5 degrees. So we can write this as that. Okay, so this is the maximum angular size that we can see with our eyes, unaided eyes, okay, without any glasses or anything, for the normal eyes. Now, if we use a magnifier, so for example, let's consider a magnifying glass. So magnifying glass is a convex lens. So let's say we have a convex lens, okay, and it has some focal length. So that's the focus, the focal point, and the distance between focal point and the optical center O is called focal length. That's the focal length. Now in magnifying glass, usually we place the object near the focal point, okay, somewhere here in between focal point and the optical center. It's placed closer to the focal point. And we usually use magnifying glass to magnify the smaller objects. So we use we observe a small object with the help of magnifying glass to magnify it. So we know from our previous lecture, if a ray travels parallel to this principal axis, so let's say a ray hits the lens parallel to this principal axis, then it will travel through the, it would go through the focal point, okay? So this will go through the focal point. And if the ray goes through the optical center, it will go straight without being refracted. If I draw a line like that, it goes straight like that. Okay. So these rays will never meet on this side. They are diverging. Okay. So these rays are diverging. That means I need to, in order to see the image, so let's say my eyes are here, okay, to see the image of this object, I need to produce these rays backwards. Okay, when I produce these rays backwards, they will meet at some point on this side of the lens. So let's see, produce them backward. Okay, and when you produce the rays backward, you need to draw a dashed line instead of solid line. So you can draw a dashed line. So just draw a dashed line. And the image formed in this way is called virtual image because it's not the real intersection of the refracted rays. And the intersection is above the axis, so the image is upright, like we said before. Whenever it's above the axis, it's upright. So that's the upright image. And you see that it's highly magnified. This is the object, and this is the object. This is the image of that object, which is highly magnified. And it's also upright. Okay, these are the characteristics of the image.
You would produce the rays backwards at an angle.
Produce backward what?
You would produce the rays back at an angle.
What do you mean by angle?
Are they going parallel?
Yeah, they should be going straight. I didn't draw it perfectly, but this should be just draw draw it like straight back, okay?
If they're parallel all the way throughout, how can they repeat?
Here, they are diverging, right? A little bit of diverging. So if I draw it perfectly, it would meet maybe even farther than that. It would make even bigger. I didn't draw it perfectly here. So this should be just drawn straight, okay? They would be converging at some point. So maybe I didn't draw it perfectly here. Do you want me to redraw that?
No, just double checking. I thought they were perfectly parallel and they.
No, these are not perfectly parallel. If you place at the focal point, they will be perfectly parallel. They will form at infinity. Okay, they will never meet. So, but if you place between O and F, they will meet at some point here. Okay. I didn't draw it perfectly, but I mean, let's see if I can draw it straight real quickly. Okay. So that's the focal point. So you need to draw the same distance on both sides, okay? Do not draw on equal lengths. So if you draw unequal lengths, you may not get the right image. And then you place a small object in between F and that, and this object is usually near the focal point. Okay, you pass it through the focal point. Okay, and another one, it goes straight like that without bending. So these are diverging on this side, you need to produce them backwards. Okay, so you need to draw them just straight. Okay, looks they are straight. Okay, and then you draw this one also straight. Okay, okay, more or less straight. You need to use a ruler to do that. Sometimes it's hard to do that on computer. So and then this would be your image. Okay, and then you don't need to draw these lines. You can only draw up to that point, okay? And these ones you need to draw dashed lines, okay? So now, what about the magnification? How do we find magnification of the image formed by a magnifying glass? So let's talk about that, okay? Now you see here, this is the image formed by magnifying glass, and the angle subtended by this image is that. So that image subtended by the, the angle subtended by the image. Now, how do we find that? So there are two ways we can find that. One is by using this big triangle. So we have this big triangle, okay, which would give you tan theta is equal to this height of the virtual image, okay, height of the image over the distance between the lens and the virtual image. You can call it what, D, okay. So that's tan theta. Or you can also use this small triangle. It would also give the same angle or same tan theta. Okay, so you can use either big angle, big triangle, or a small triangle. So this would give you h. H is the height. Okay, height of the object. Now see the difference when you consider the bigger triangle. Tan theta is given by this height, okay, which is the height of image, and this distance, which is we call di. But if you use smaller triangle, this one, Then tan theta is given by opposite of that angle, which is h. In this case, h is the height of the object, not image, okay? And then this distance, this is the base, okay? Now this, we already said that we usually place the object pretty close to the focal point. This is the focal point. So we can just assume that or approximate that this distance is the focal length, okay? It's not exactly focal length, but since it's pretty close to the focal point, we can assume that this is focal length, okay? So that's this adjacent. Is that called adjacent? This base, I usually call this distance base in a triangle. What do you call this side of the triangle? Is that adjacent or? Okay, so that's the adjacent, F naught. So this is, we should write this approximately, okay? We are just assuming that this distance is F naught. Or in this case, you can just write F, you don't need to write F naught, okay? And for small triangle, we can write this as, or small angle, we can write this as theta equal to h over f, okay? Again, we are here getting tan theta is equal to this height of the object over this distance, which is more or less equal to f, focal length of that length, okay? So h over f is the magnification or angular size. This is the angular size with the aid of a magnifying glass. If you guys remember, the angular size without using the magnifying glass is, do you guys remember what that is? We just talked in the previous slide. Theta naught is angular size without using glass, any external devices. This is the angular size with this lens, but without using lens, what's the angular size? Without naked eyes. We just talked about this in the previous slide. Okay, let's go back. So that's the, yeah, so h over 25, right? So this is the angular size without using any lenses. So h over 25. So that means, what's the magnification? Magnification of a magnifying glass. So let's see. So we define magnification, like I said in the very beginning, magnification could be defined as theta over theta naught, okay? Where theta is angular size with the lens and theta naught is angular size without the lens. And we found that theta is, what is theta? We just got it, huh? H over F, right? And theta naught is, what is that? H over 25, is that right? So that means M is, we can cancel H and H. This 25 will go on the top, do the math, 25 over F, 25 centimeter over F. So that gives us the magnification of a magnifying glass. Okay, which is also called angular magnification. Now we will need this to deal with the microscope, okay? So please remember this for the next part. So angular magnification of a single convex lens is 25 centimeter over F. Now let's talk about a microscope, okay? So microscope has two lenses, unlike the magnifying glass. So that's the microscope. It has a lens that is near the object, which is called objective. And objective has relatively shorter focal length than the second one. Okay, this is called objective, and we have another lens which is near the eyes, and it's called eyepiece. It has a relatively longer focal length. So this is called eyepiece, and this is called objective. And it's easier to remember because this is near your eyes. Your eyes would be somewhere here, and this is near the object. And this has the focal point, and that's the focal length, okay, shorter focal length. This distance is the focal length. And this one has longer focal length. Now, because we have two lenses, so we need to differentiate the focal lengths or focal points. So this is the focal point of objective. So we write this f sub O, f sub O. This is f sub E, f sub E. Okay. Now, usually in microscope, smaller objects are placed near the focal point, okay, somewhere here. And so if you draw a straight line passing through straight line parallel to this axis, it will go through the focal point. Okay, so it'll go through the focal point of that lens. And then if you pass the ray through the center, optical center, it will go without refraction. And they will meet at some point here. And it's below the axis, so the object, the image form would be inverted, upside down. So that's the image of that small object formed by this objective lens. Okay, when you draw it, you need to draw the arrows to show which way the light is going. Now this becomes the object for this eyepiece. Okay, so this is the image of the objective, but this becomes the object for this lens. So for this one eyepiece, if you draw a straight line parallel to the axis, so by the rule, it needs to go through the focal point. So that will go to the focal point. Okay. And then if you pass it through the optical center, it will go without bending, like that. Okay. So your eyes are somewhere here. Okay. Now, in order to see the image, these rays need to intersect on this side to form the real image. But they are diverging from each other, so they will never meet on this side. That means you need to produce them backwards. Okay, so produce the rays on this side, that one also, this side, and they will meet somewhere here. Okay, and that's the point where the image is formed. So whenever you produce the lines backward, you need to draw just the dashed line, not the solid line. Okay, and our image is here. So that's the image due to the combined lenses. So that's the object, and that's the final, I should say, final image. And one thing I would like to mention here, the distance between the image formed by this objective and this objective lens is called tube length, okay? So usually these are within that tube of the microscope. It is L. If you have a tube in your microscope, usually these two things fit within that tube. So the lens would be somewhere here, and the image is formed somewhere here for this objective. So this is for the objective. So this distance is the tube length. Now, what's the magnification of this microscope? We need to find the magnification. So when we find the magnification of a combined system, we have two lenses, then we find the magnification as the product of magnification due to this one, which is MO, magnification due to objective, and magnification due to this piece, okay, which is ME, magnification due to the eyepiece. So the product gives you the total magnification. So what's that magnification? So let's look at this one, objective. Magnification of objective. Do you guys remember from the previous one? Magnification, this objective is just like a magnifying glass, okay? So the object is placed near the focal point. In the previous one, we placed it here, but here we put it here. So that's 25 over f, right? And in this case, f is the focal length of the objective. So that's the magnification of this single lens. And the magnification of eyepiece, from the definition of magnification, we have two types of magnification. One is linear and the other one is angular. So we can use here, we don't have the information about the angular size. Okay, it's hard to get angular size here, although it's possible, but it's easier to get the information about the distance, okay, linear distance. So we will use this formula. So if you remember, magnification is image distance, S prime, over object distance. Now, what is the image distance here? What's the object distance? So usually, if I didn't draw it perfectly here, if I show you another picture here. So see. Here, I think let me. Okay, here, let's see. Okay, it's the eyepiece here. It's the eyepiece that acts as the magnifying glass. Okay. So I think I just said it opposite to what it's supposed to be. So if you look at this picture, because my picture was not like perfect. So in this case, this is the eyepiece. And in this case, this eyepiece acts as a magnifying glass. This object is pretty close to the object or the focal length, focal point. Okay, this acts as magnifying glass. That means the magnification of this one, E would be 25 over FE. Okay. So that's the magnification of eyepiece. Again, this acts like a magnifier, a magnifying glass. Now for this one, the magnification of the object would be negative. Okay, that's from the definition, S prime over S. Okay. In this case, the image is formed here. Okay, and this distance is the tube distance or tube length, which is L. So this part fits within the tube. If you have a tube like that in the microscope, that part fits within the tube, which is the distance L. So the image distance is L, tube length, and S is, now this is the object distance. That is the object distance, S, but it's pretty close to the, sorry, that's the object distance, okay, from the object to the lens. And it's pretty close to the focal point. So we can approximate that distance as F naught. So we can write that F naught. Okay, it's not exactly F naught. F naught is this distance. Okay, that distance is F naught. But because this is pretty close to the focal point, so we can just assume that's F naught. Okay, object distance is F naught. So we have this magnification due to the objective, and this magnification due to the eyepiece, and the combined magnification M would be M naught times ME, which is, we also have minus sign here, which would be minus L F naught, okay, times 25 over FE. Okay, so that gives us the total magnification, minus 25 L over F naught FE. Okay. So let's look at a problem application of this. Okay. Again, so this is the magnification. And this minus sign shows that the image that we get would be inverted. The final image is inverted. Okay, so here is an example. We have a biological microscope whose objective is labeled as 20x. What is the focal length? What is its focal length? So this is about objective only, okay? We have eyepiece and objective, but in this problem, we are dealing only with the objective. So for objective, if you remember, the magnification of objective is, oops, what happened? What is the magnification of objective? That's the magnification of objective, okay? So minus L over F naught, okay? And magnification is 20 times, okay? And then L would be the tube length. Generally, the tube length is not given here, but the standard tube length is about 160 millimeters. Okay, so that's the standard tube length. And this would be negative magnification. If you see the image here, the image formed here is inverted for the objective, right? This is the objective, and it formed inverted image. And if you remember from the sign convention we used last time, whenever the image is inverted, the magnification is negative, okay? So M would be negative when it's inverted. So we need to write 20x, okay? So that's the magnification. This minus comes from the fact that the image is inverted. So our magnification is minus 20 times, and tube length is 160 millimeters, and over F naught. So F naught would be minus 160 millimeters over 20 millimeters, 20 only. So that gives me minus, and minus also cancel. So 8 millimeter. Okay, so the focal length of the objective here is 8 millimeters. Let's look at another problem here. Now this one has both objective and eyepiece. A student uses a microscope to view an amoeba. If the objective has the focal length, so we have FO is 1 centimeter, and the eyepiece has the focal length of 2.5 centimeters, and the size of the amoeba is 1.1 centimeter. No, sorry. The amoeba is 1.1 centimeters from the objective. So that's the distance between the amoeba and the objective. Okay. What is the microscope's magnification? We need to find the magnification. And we know from our previous slides, magnification is ME, MO. And ME is, what's the magnification of eyepiece? (25 over FE), and that's minus, what is that? L over F naught. Okay, good. So let's see, 25 F, oops, 25 FE is, let's see, what's FE? 25 over 2.5. Okay, I'm not writing the unit here. This is centimeters. And then L, tube length is, again, if it is not given, then the standard tube length is usually 160 millimeters. So 160, now we need to change it to centimeters because this is in centimeters. That's times -2. Okay, that's now in centimeters. And then FO is 1 centimeter. So that will give us the magnification. So let's calculate that. Can you guys do the math? So this will be 10. It should be 16, I think. Maybe. Is that 16? Yeah, that should be 16. Is that 16? Yeah, you're right. So there is negative sign here. I don't know why it's doing that. Minus 16, 16 times. Okay. So that's that. Now let's talk a little bit about dispersion. There is a phenomena in which light is split into its constituent colors. If you pass the light through a prism, the light is split into its 7 different constituent colors. So those 7 constituent colors are red, orange, blue. Okay, so its acronym is ROYGBIV, ROYGBIV. Red, orange, yellow, green, blue, indigo, and violet. Okay, you get 7 different colors. This was first shown by Newton about 400 years ago. And if you combine, if you place another prism in this opposite orientation, then these rays will again combine to give you a white light. Okay, so that means white light is made up of 7 different colors. So this kind of phenomena is called dispersion. So this separation of color through the prism is called dispersion. Now, if you filter the color, and if you just pass one color to the prism, let's say in this case green color to the prism, then you will only see the green color through that prism. Okay? That means this separation is not actually due to the prism. It's the intrinsic property of the color, because the intrinsic property of the light. Okay? Because the light is made up of 7 different colors, white light. That's why it got separated when it passes through the prism. Okay? Now, what's the application of that? So the rainbow that we see is actually due to this dispersion principle. So what happens when sunlight hits water droplets is, when the sunlight hits the water droplet, there is dispersion of the colors. Okay, so the colors get separated inside the water droplet. The water droplet acts as a prism. And on the back of the water droplet, these rays go through total internal reflection. There is TIR. Okay, so these rays are not refracted to the air. Instead, they are reflected back in the same medium, which is TIR. And then when the colors come out of the water droplets, once again they are refracted, okay, spreading them into wider angle. So different colors are dispersed at different angles. So for example, when the light hits on the water droplet, red colors are usually dispersed at 42 degrees, and violet colors are dispersed at 40.8 degrees. So that means the color that you see come from different water droplets. So the red comes from this water droplet, and the green comes from this one because it's dispersed at different angle, and the violet one comes from this one. Okay, again, this is one application of dispersion. I think that's all for this chapter. Now, next time we will start a new chapter, very exciting chapter, charge and electricity. If you guys have any question, we still have a minute left.